Okay, so welcome to Math 310, Introduction to Modern Algebra. What I want to do today is talk about where do things go from here. If you were to take a second course in the subject, what would you see? So I want to try to finish rings and talk about one of the big applications of all this, solving polynomials. So some of this is stuff that you've seen before, some of it is going to be new. For those of you who want more details, to make up for the couple of minutes missed from today and last time, I've given you links to two videos that go through and do a nice job of talking about Galois theory, where the group theory that we're doing comes into play in terms of figuring out why we can't write down closed form expressions for roots of certain polynomials. And this is a really interesting question. How can you prove that you can't do something? Okay, so I'm not going to go into too much detail in all of this. Just very briefly, just like we have groups and subgroups, you could have rings and subrings. We can also go in the other direction. Rather than looking at a subset, we could look at a superset. So we could look at an extension of a group. We can look at an extension of a ring or an extension of a field. And so here, we're going to talk about an extension L over field F. So L and F are both fields. And so we can choose some elements, let's say alpha 1 through alpha n, that are in L. Then there's a unique field with the following properties. The field K lives between F and L. The elements alpha 1 through alpha n are in K. And then if K prime is any field between F and L that contains alpha 1 through alpha n, then K is contained in K prime. So, there's a smallest field that has these properties. Informally, what you're really doing is you're basically saying, look, let me take these elements alpha 1 through alpha n, let me put them in, and then put in whatever else I need to keep something a field. So what's the big property you think that's going to be important to think about? Any thoughts about what properties, when we add an element? So we have, the field of the rationals, and then we have the field of the complex numbers C. So, whenever you have a theorem, let's try to make it explicit. Let's choose an element that is complex but not rational. So let's take maybe the square root of 2 and the square root of 3. And we want them to be in our field K, and we want K to live between the rationals and the complex numbers. And so what elements do you think might be difficult to ensure that we have? So remember, a field is a special type of ring. So if I give you some elements in a ring, what must be true about elements in a ring?
They should have an additive and multiplicative identity.
So they should have an additive and multiplicative identity. So is there a K in K such that, K square root of 2 equals 1? Because again, since it's a field, every non-zero element has to be invertible. So as soon as we get that, that tells us that 1 over the square root of 2 has to be in our field K. So as soon as we add square root of 2, we have to add 1 over the square root of 2. What else must be true about what other element must be in the field?
Additive inverse, and every element should have a multiplicative inverse except 0.
Okay, good. So we've just done multiplicative inverses, but I've given you square root of 2 and square root of 3. What other elements must be included as soon as I give you root 2 and root 3?
Root 2 plus root 3.
Yeah, so root 2 plus root 3 has to be in K, or m root 2 plus n root 3 for all integers m and n. Because I can just keep adding root 2 to itself, I can keep adding root 3 to itself. But now I know 1 over root 2 is in this ring. And so square root of 3 over square root of 2 has to be in K. And so the question becomes, is there a simple formula for everything that's in this field? So for example, can I write it as maybe A plus B square root of 2 plus C square root of 3? And can you think of any other number that might be useful to include?
Square root of 6.
Yeah, square root of 6. So here's my question. If A, B, C, D are rational, does this form a field containing square root of 2, square root of 3 is its smallest? I know I clearly need stuff of this form. The question is, do I actually need a square root of 6? Could I get, is square root of 6 equal to A plus B root 2 plus C root 3 for some A, B, C rational? And so as a nice exercise, extra credit, figure it out. Is it possible to write square root of 6 as a combination like this, or do we really need something new? And so again, a lot of the stuff in the subject, if you continue going further, is to try to figure out, if I add a couple of elements, how big of a space do I get? How much do I extend things? Okay. And then if K is a extension of a field F, we say the degree of K over F is the dimension when we view it as a F vector space. So what we might be able to write is maybe there exists, elements, let's say K1, K2, dot, 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 K, and I'll denote this by N, in K, such that for all K in K, there exists F1 through Fn in F, such that K is equal to F1 K1 plus dot, 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 plus Fn Kn. That we can write any element as a linear combination of these basis vectors. And so there's a whole deep theory about stuff like this. And if I give you a field, can you find a basis? Is the basis unique? Almost surely not. But one thing that should be true is if I give you two different bases, they should have the same dimension. And so one of the big questions is always which properties are true no matter which representatives do you use and which ones depend. So let's do some linear algebra review. If I give you two-dimensional space, can somebody give me a basis for two-dimensional space for R2?
1, 0, 0, 1.
Okay, so you have given me the canonical standard basis. What about the following basis? Would this work? So one of them is going to be 1, 0, and the other one is going to be 1, 1. Would that be a basis? Yeah. This is a basis as well. They have the same number of basis vectors. So the number of basis vectors is the same. But in the first, the vectors are orthogonal or perpendicular, not in the second. So we don't have to choose an orthogonal basis. We don't have to have all the basis elements at a 90-degree angle from each other. So that's not a property that must always be true. But we're never going to find 3 linearly independent vectors. And then there's a lot of theorems that are similar to what we saw in group theory. And so this is why I don't want to spend too much time going over this. So we're talking about now a tower. So we have a field F, and then we have a field K over F, and then we have a field L over K. So think of F down here, and then above it is some field K, and above that is some field L. And we can talk about the dimensions of one over the other. So we can ask, what is the dimension of L over K? That's just some numbers. How many independent directions do we need? And we can talk about the dimension of K over F. But we could also ask, what is the dimension of L over F? And then how is L over F related to the degree of L over K and the degree of K over F? And the result is what I think you should expect. What you think is true turns out to be true. It's just multiplicative. So answer equals the product. And we had a result similar to this in group theory. And so if one of the extensions is infinite, L over K or K over F, then L over F is also infinite. And this is a big question, is when do you need infinitely many elements? When do you only need one? So for example, we could have, let's say, the reals, oops. And we could have the complex. Anybody want to guess what the degree of the complex numbers are over the reals? So what do you think the degree of the complex numbers over the reals would be? So this means given some z in C, I want to write z as, let's say, R1 C1 plus ... plus Rn Cn. How many basis elements do you think I need to get the complex numbers from the reals?
Two.
2. So this should hopefully be 2. And what might be a good basis? What's the standard basis we use for complex numbers?
1, 0, 0, I. I don't know.
Yeah, so we could just write it as 1, and we could write it as I. And so it's clear that this is going to be a basis. Well, it's clear that it's going to be spanning. Let's be careful. Let's use the correct linear algebra words. Anything can be written as a linear combination of 1 and I. The question is, can we do better? Can we do it with just one complex number? And so I'll leave that as an exercise. Prove this is a basis. And you can do this by show, C does not equal all the reals times some fixed number for any fixed complex number C and C. So we know we can write all the complex numbers as a linear combination of 2 elements. The only way this would not be a basis is if there was a way to do it as just 1 element. So you have to show that if you choose any complex number C and you look at all real multiples of it, there's some complex number you miss. So again, this would be a good problem to write up rigorously. So, try to write this up rigorously. Now, can somebody give me a field that the real numbers contain? So we've already seen this field today.
The rationals?
The rationals. And then you could ask, what is the extension of the reals over the rationals? And that turns out to be infinite. You can't add just finitely many rationals and get finitely many real numbers to the rationals and get the reals. So another nice exercise is try to write this up rigorously. Prove this. So all you have to do is show that if you have finitely many real numbers, the linear combinations and all the stuff, all the closures, is not going to be enough to get all the real numbers. So things get really complicated. Okay. So a lot of the way we make progress is we study polynomials. So let f be a field, and then f of x we'll write as f bracketed x is a non-zero polynomial. If we have a zero polynomial, it's kind of boring. So we can write the polynomial as a0 plus a1x all the way up to a dxd. And the convention is typically going to be that the last coefficient, when we write it like this, is going to be non-zero. If I multiply two polynomials, what do you think should be true about their degree? So if I give you f of x equals, the sum, let's say n goes from 1 to d of, an x to the n, and g of x is the sum m goes from 1 to, call that maybe d1, we'll call this d2 of bm x to the m. What do you think the degree of fg should be?
D1 plus D2.
Is that always going to be true?
Not in Z and Z fields.
Well, so why might it not be true in a field? So we know when we look at f of x times g of x, it's going to be a d1 b d2 x to the d1 plus d2 plus lower order terms. All we need to know is this is non-zero. So if I give you two numbers that are not zero and I multiply them in a field, is it non-zero? So if I take two elements in a field and both elements are not zero, is their product non-zero?
Yes.
Yes, this is the whole property of field. Yes, as a field. What if I just gave you a ring? Is it possible that the product could be zero in a ring? Could you give me two numbers that are not zero that have a zero product in a ring? What's
2 times 3 in Z 6Z.
Sure. So if we do, z mod 6z, 2 times 3 is 0 mod 6. So degree can be lower in a ring. So whenever you see a definition, you always want to focus on, are these conditions necessary? Do we really need f to be a field? Well, we're still going to have a lot of results if f is not a field, but it's good to try to get a sense of where might this be useful. And so the degree of a polynomial is going to just be the highest power of x. And this has the nice property that the degree of a product is the product of the degrees. This would not be true in general. Now, if you look carefully, you see that we set the degree of 0 to be negative infinity. Can anybody think why would we set the degree of 0 to be negative infinity?
Maybe if you're doing arithmetic with degrees, you would want the degree of 0 to be lower than all possible additions of degrees.
Okay. So what property do you want the degree of f times g to satisfy? The degree of a product we just answered it here, right? The degree of fg was d1 plus d2. So what should the degree of a product equal?
Sum of the degrees.
Sum of the degrees. So that should be the degree of f plus the degree of g. Does this look like any maps you've seen before? Where have we seen something like this?
Homomorphism.
Yeah, this looks like a homomorphism where over here it's multiplication and here it's addition. It's a different group law, it's a different composition law, but it does look like a homomorphism. So imagine g of x is the 0 polynomial. Then we want the degree of f times the 0 polynomial to be the degree of f plus the degree of the 0 polynomial. Well, this is the degree of the 0 polynomial equals the degree of f plus the degree of the 0 polynomial. There's only two choices that work for the degree of 0. What are the only two choices that work? One of them you should get just from looking at this.
Negative infinity.
Negative infinity. So either the degree of 0 equals negative infinity, or what's the other possibility?
Infinity.
Infinity. And it makes more sense to choose it to be negative infinity because it should be of a lower degree than everything else. And so a lot of times there's good reason behind the choices we make. So there is a reason why we're choosing the degree of 0 to be negative infinity. It allows us in the expanded notion of numbers to have this relation, the degree of a product is the sum of the degrees, to still be true. This might be similar to we choose 0 factorial to be 1, or we choose negative 5 factorial to be infinity. These are just good conventions to allow us to continue. Okay, so we've seen the Euclidean algorithm and how useful it is. It turns out you can do something similar with polynomials. And if I give you a polynomial f and another polynomial g, we can ask how many times does g go into f? And there'll be a remainder, and the remainder will have smaller degree. And it's very important that we have a field so that we can invert the leading element of f. So, if f of x equals, an x to the n plus dot 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 plus a1, and g of x equals, say, bm x to the m plus dot 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 plus b0, without loss of generality, let's assume m is less than or equal to n. So we want to ask, how many times do we multiply g of x to get f of x? And we might start with looking at, an over bm x to the n minus m times g of x is going to be equal to an x to the n plus dot dot dot. And so we can see that we can, by multiplying like that, we can start getting something that looks like f of x. And so, again, you can put in all the details to make this rigorous, but it does seem natural that we should be able to extend the Euclidean algorithm. We should be able to extend, hopefully in a lot of cases, what's going on. Notice how crucial it is that we're in a field. So we need a field, so 1 over bm exists. If I was looking at z mod 12z and f of x started off as 4x to the n, I can't invert 4. Or g of x started, 4x to the m, I couldn't invert the 4. Okay, and now there's lots of different stuff that you can prove. I'm not going to go through all of the details here. It's just worth knowing what's out there. So if you do decide you want to go off to math graduate school, you've at least seen a little bit of what there is. And if that is something that is in your cards, talk to me and I'm happy to meet up with you and go into more detail for stuff like this. Then there's stuff about finite fields. Again, I'm not going to really go into much detail about that. I want to talk about the structure of various numbers and which polynomials can we solve explicitly and which can we not. So hopefully these two are not surprising. If I give you a linear equation, ax plus b equals 0, this isn't that hard to solve. We move b over to the other side, divide by a. So in all of these, we will always assume the coefficient of the highest degree is non-zero. If I give you a quadratic, ax squared plus bx plus c equals 0, we get the roots of negative b plus or minus square root of b squared minus 4ac over 2a. Do people know how to prove the quadratic formula? Can everybody prove the quadratic formula?
I know I saw a proof for it on the complex plane once, but I don't remember it.
All right, so let's give a proof. It turns out that there are formulas for cubics and quartics, but not higher. And so let's do things in stages. If I give you ax squared plus c equals 0, this is not that bad to solve. This is the same as ax squared equals negative c, x squared equals negative c over a, x equals plus or minus the square root of negative c over a. So we can solve something like that without too much trouble. The next question is, what should we study next? If I give you ax minus h squared plus c equals 0, the solution is almost identical. It's x minus h squared equals negative c, x minus h squared equals negative c over a. So x is equal to h plus or minus the square root of negative c over a. You might have seen this long time ago in Algebra 2. It's related to vertex form for parabola. If you can write something like this, it's very easy to find what's the coordinate of the x-coordinate of the vertex. So more generally, if I give you ax squared plus bx plus c, let's try to write that in the form ax minus h squared plus c. And these might not necessarily be the same a and c, so I'll put tildes on them. Can we find something that works? So maybe it's better to put, oh yeah, we'll leave it like this. Because if I can get something of this form, I know how to solve it. So the typical method is called completing the square. So we can write ax squared plus bx plus c as ax squared plus b over ax plus c. And whenever you write something with a big space like this, it's because we're going to be putting something in. And so I can put in b squared over 2a squared and subtract b squared over 2a squared. And now what we have is this is going to be a x squared plus b over a x plus b squared over 2a squared minus b squared over 2a plus c. But this is just x plus b over a squared. And then this is going to be minus b squared. It seems like, have I made an algebra mistake? Oh, sorry. These should be 4s, not 2s. So that should be a 4a squared and a minus 4a squared. And now, when I put in 4a squared, it's going to be b over 2a. And now when I do FOIL, I'm going to get x squared plus twice b over 2a, which is b over a, plus b squared over 2a squared, which is b squared over 4a squared. So this should be a 4a over here, so it's b squared minus 4ac all over 2a. And so we then get a x plus b over 2a squared equals b squared minus 4ac all over, and this is 4a. I can move this a over to the other side, and we'll get x plus b over 2a squared equals b squared minus 4ac over 4a squared. And so now we have x plus b over 2a squared was b squared minus 4ac all over 2a squared. So x plus b over 2a is equal to plus or minus the square root of b squared minus 4ac all over 2a. And now just bringing the b over 2a to the other side, we get negative b plus minus the square root of b squared minus 4ac all over 2a. So by looking at simpler polynomials, simpler quadratics, we saw how to solve those without too much trouble. And then we just took our general quadratic and we put it in that form, we put it in that vertex form. And so by completing the square, we made things much, much easier. So there's a trick like this that allows us to find the roots for a quadratic. And then the question is, what about cubics? What about highers? So this is the 3 solutions to the cubic ax cubed plus bx squared plus cx plus d. It would be a nightmare if you had to memorize this. Are there any simplifications you could do to make this a little bit easier to use? No. Without loss of generality, what can you choose A to be?
One.
1. You can divide through by A. So you would replace, B with B over A, C with C over A, D with D over A. And it turns out, without loss of generality, you can assume B equals 0 by just doing a translation. That will make this a little bit better. It's still a nightmare, but it makes it a little bit better. This is an explicit formula. You give me any cubic and I have the roots. Here's the quartic. This is only one of the 4 roots. You've got square roots inside square roots, I believe. Maybe not. Yes, we do. We have a root over here. This is a nightmare. What could you do to make things a little bit easier?
A
What could-
equals 1.
A equals 1 and B equals 0. So we can always translate a little bit. We can basically just, replace x with x minus r to shift roots can move to a new polynomial with b equals 0. It's still a nightmare. So the question is, what if I give you a degree 5, a degree 6, a degree 7? Can we find the roots? And it is a deep theorem that the answer is no. There is no explicit closed form solution that gives you the roots as a function of the coefficients and your radicals, square roots, cube roots, stuff like that. So in general, it's very hard to find exact answers. We can, however, approximate. We can find things that are close. And so what I want to do today is talk a little bit about computational mathematics. So imagine I give you a continuous function, and I know it's negative near 0, and I know it's positive near 1. What must happen?
It must go to 0 somewhere in between.
Yeah, so it must cross the x-axis between 0 and 1. How many times must it cross?
At least 1.
At least 1. We can do better. Could it cross 2 times? Would it be possible to go like that?
Yes.
Let me rephrase. Is it possible to cross only 2 times? So it starts negative, crosses exactly 2 times, and has to end positive.
No.
No, it's got to get back up to 1. So what do you know about the number of crossings?
It's odd.
Yeah. So number of crossings is odd. So if I give you a polynomial for a continuous function, and it's negative at one point and positive at another, then we know there have to be an odd number of crossings. We can use this to find approximations to the roots. So this is the method of divide and conquer. And so what we do is, we take our interval. So here's A, here's B. Let's say it's positive at A and negative at B. We look at the middle point. Imagine it's positive here. Where must there be a root? In the first half or the second half? So where must, in the second half. So this is the intermediate value thing. So then we look in the middle here. So there must be a root. Let's say it's negative over here. Then we would look over here. And so every time we do this, we cut things in half. Okay? And so we're going to get smaller and smaller intervals in which the root lives. So let's try to figure out how quickly things are converging. So if we do 10 times the size of the final interval is original length divided by 2 to the 10. Does anybody know approximately what 2 to the 10 is?
About
Approximate. Yeah, it's approximately 1,000. So what this tells you is 10 iterations is approximately 3 decimal digits. So if you wanted 3 decimal digits, if you did this 10 times, you should get about 3 decimal digits. If you wanted to get 20 digits, if you wanted to get 6 digits, you would have to do it 20 times. Is this good or bad? It is what it is. Whether or not it's good or bad depends on what do other methods give us. So I can't answer this question in isolation. I have to compare it to others. I just noticed there was a question in the chat on a degree of polynomials. So let me just go back a little bit. So the question was, what is the degree of a constant? So any integer except 0. Well, let's say g is constant. Let's say g of x equals c, which does not equal 0. We want the degree of f times c to equal the degree of f plus the degree of c. So the degree of f times c is the same as the degree of f. Because c is a constant, it doesn't change the power of the highest degree. That's equal to the degree of f plus the degree of c. So what's the degree of c? What's the degree of our constant?
0.
Has to be 0. So all non-zero constants have a degree of 0. And if you think about it, I am using in this argument the fact that I have a constant that's not 0. I'm using that to say the degree of f times c is the same as the degree of f. If it was actually 0, then f times 0 is just 0. So you always want to ask, where am I using the assumptions? Where am I using the features of the problem? Okay. If I do miss something in the chat, just let me know. All right. So we did divide and conquer. We talked about every 10 iterations gives us 3 decimal digits. So let's take the square root of 3. It's about 1.732. Made a simple Excel sheet to calculate, keep taking the left and the right intervals. And we see after 10 iterations that the answer is somewhere between 1.730 and 1.732. And we are basically getting 3 decimal digits for the square root of 3 after 10 iterations. And we're starting by saying the square root of 3 lives somewhere between 1 and 2. So that's not a terribly great starting point. I'm not really stacking the deck in my favor. I want to show you a much better way to find or to approximate answers. So this is the problem that really pushed me from physics to math. It's one of the most powerful things I've seen in my life. So we've been doing a lot of review of linear algebra. Let's quickly review calculus. So one of the most important uses of calculus is to approximate a curve by a straight line. This is the tangent line approximation. And so the idea is that locally, any differentiable function looks like a straight line. If you're driving on the highway and I know your instantaneous speed, I can figure out where you will be a split second later. Where you'll be an hour later is very different. But in a small amount of time, there really shouldn't be that much change. And so basically the new location f of x is the old location f of x naught plus the instantaneous speed f prime of x naught times the elapsed time x minus x naught. And so we can get a really good equation. We can get this by using the point slope form. So we have the point that's on the curve x naught f of x naught, and the slope is just f prime of x naught. So this is hopefully something that was covered in your calculus class, that we can approximate functions with straight lines. So for example, if I give you the function 2x cubed minus 3x plus 1, I can calculate the derivative. It's going to just be 6x squared minus 3. And if I give you some point 4, I can then calculate what is my tangent line. And if you look at the tangent line approximation, I think you'll agree it's doing a pretty good job. This tangent line approximation, even if I go all the way down to 3.5 all the way up to 4.5, it looks pretty close. If I'm even closer from say 3.9 to 4.1, it's really close. It's hard to tell that there's even a difference. So the tangent line approximation locally does a good job. And we can use this to create a method to find or to approximate roots of polynomials. And so this is Newton's method. It is absolutely amazing how well this works. So assume f is continuous and differentiable. So this is more than the divide and conquer. In divide and conquer, we just assumed our function was continuous. Now we're assuming the function is continuous and differentiable. We shouldn't be doing worse if we assume more about our function. And the idea is now that we have more at our disposal, we expect to be able to get a better result. And so we're going to generate a sequence, hopefully converging to the root as follows. So given some point xn, we'll look at the tangent line to the curve y equals f of x at that point. It has slope f prime of xn, and it goes through the point xn f of xn. We get the tangent line, and then we see where that line hits the x-axis, so when y equals 0, and it gives us a new point. And then just lather, rinse, repeat. So just to draw a little picture, we start off with some point x naught. We get a point on the curve. So this is the point x naught f of x naught. And the slope of the tangent line is just f prime of x naught. And now we calculate the tangent line. So it's y minus y naught equals m x minus x naught. So y minus f of x naught equals m x minus x naught. Oops, and m is f prime of x naught. Let me just erase so you got space to write it. Is f prime of x naught x minus x naught. So that's the equation of the tangent line. And then we can ask, where does this tangent line hit the x-axis? It's going to hit somewhere. Where does it hit? And so it hits at a point that we'll call x1, and the y value is going to be 0 because we want it to hit the x-axis. So we would get 0 minus f of x naught equals f prime of x naught x1 minus x naught. So x1 minus x naught is negative f of x naught over f prime of x naught. So x1 is x naught minus f of x naught over f prime of x naught. What's the main worry we have right now? when you see this, what should you be afraid of?
F prime being 0.
F prime being 0 at x naught. So we need f prime of x naught is not 0. So if we were going near a double root, we would have trouble. But as long as we're not near a double root, we're going to be fine. And so this gives us a new point. And then we can play the lather, rinse, repeat game. We can then find, what's the value of the function at x1? Is it 0? If yes, great, we found the root. If not, we play the game again. And so this is showing what happens after 2 iterations. We had x0 to x1, x1 to x2, and you can see it's getting pretty close to the root. And the fundamental idea is that the tangent line should be a good approximation. So if you just say, my instantaneous speed is always my correct speed, and just flow in that direction and see where you would hit. The hope is that if you do this a couple of times, it's going to be close. So how close? So we did some algebra, and we saw that, x1 was x naught minus f of x naught over f prime of x naught. More generally, xn plus 1 would be xn minus f of xn over f prime of xn. So if we're looking at the function f of x equals x squared minus 3, the roots are plus or minus the square root of 3. So this should hopefully find a way to approximate the square root of 3. So f of xn is going to be xn squared minus 3. F prime of xn is going to just be 2xn, as f prime of x is just 2x. So we can plug this in. And so, substituting these in, this gives xn plus 1 is xn minus xn squared minus 3 over 2xn. And after we do a little bit of algebra, we'll get to the equation down here. We'll get xn plus 1 is 1/2 xn plus 3 over xn. Whenever you see a formula, you always want to ask, is this reasonable? It's telling you what should your new guess be as a function of your old guess. If you were really lucky, what would be a great value for xn to be for you?
One.
What do you think? Any thoughts?
1.
Why 1?
I think it makes the algebra easier, but no, that wouldn't make that much of a difference.
But remember, we're looking at f of x is x squared minus 3. What are we trying to find? What we're trying to find the root of x squared minus 3. Right? What's the root we're looking for?
Say that again.
So what root are we looking for?
So x squared minus 3.
Right, and what is that root?
Square root of 3.
Looking for the root of x squared minus 3 equals 0, or plus or minus square root of 3. So we're lucky if xn equals what?
Square root of 3.
Square root of 3. And notice in that case, xn plus 1 would be 1/2 root 3 plus 3 over square roots of 3, which is 1/2 root 3 plus root 3, which is root 3. It's stable. So if you find a root, you stay at the root. And then the hope is that if you're not at a root, this will move you to a root somewhat quickly. And so this is, going through again, just doing all the algebra, showing how we get it. So let's see how good it does. So here's our formula. Xn plus 1 is 1/2 xn plus 3 over xn. X naught equals 2. Does everyone agree that this is not a particularly great initial guess for the square root of 3? I'm not stacking the deck by choosing something terrific. So let's calculate x1. So x1 is going to be 1/2 x0 plus 3 over x0. So it's 1/2 2 plus 3 halves. So what's 2 plus 3 halves?
7 halves.
7 halves. We multiply by 2, we get 7/4, which is 1.75. How does that look for square root of 3?
Better.
We're getting 1.75 after just one iteration. Look at the divide and conquer. Took a little bit more time before we got something, very close to that. Let's do another iteration. Oops. Let's do x2 is 1/2 x1 plus 3 over x1. So it's 1/2 7/4 plus 3 over 7/4, which is going to be 12/7. So that's going to be 49 plus 48 over 28. So it's going to be 97 over 56. Yes? And that's about 1.73214. I have Mathematica open on my computer. After 2 iterations, we're already pretty close. And so, I just did a few more. So x3 would, it's not too bad. It's 18,817 over 10,864. It's about 1.732050810. 0508. So we have 076, and we have 100 over here. We're off by 0.00000000024 approximately. 3 iterations. 3 iterations. And we have a rational approximation of square root of 3. That's 1, 2, 3, 4, 5, 6, 7, 8. That starts off with basically 8 zeros before we finally get to a non-zero element. It's absolutely incredible how well this works. Divide and conquer every 10 iterations gave you 3 digits. Newton's method, essentially every iteration doubles the number of digits you have right. It works remarkably quickly. If you do the 5th iteration, it takes an awful long time before you finally notice a difference between them. We have a rational approximation that is almost perfect. Now, I know some of you are computer science majors, and one of the big things in computer science is we can't work with a real number. We have to work with rationals. And so we can approximate real numbers by rationals very, very well. So I want to play a little game now. So let's take the polynomial x squared minus 1. It has roots in -1 and +1. These are not that hard to find. So if we start at a point x0, do we approach a root, and which root do you think we approach? So can anybody tell me which parts of the interval they think are going to approach 1 when we use Newton's method? It's possible that it doesn't converge to any point, that if you put in certain values, you don't converge at all. You just wildly oscillate. But does anybody have any thoughts about which points might converge to 1? Any region of the line that you hope would converge to 1.
Point between 0 and 1.
Between 0 and 1, anything else? So anything between 0 and 1 should go to 1. Anything else should go to 1.
Between 1 and 2.
Okay, what about between 2 and 3?
Yes, anything above 1 then.
Yeah, so basically, the hope is that maybe all of this goes to 1. And similarly, everything below 0 should go to -1. And what about 0?
Undefined, like 1
Yeah.
over.
This is the battleground state. It's right between them. If I try putting in 0, my formula blows up. I can't use Newton's method there. Let's extend to the complex numbers. So let's say we take x cubed minus 1 equals 0. We can factor this as x minus 1, and then x squared plus x plus 1. We can use the quadratic formula, and we can get the roots. And so I'll label the roots, red, blue, and green. Any thoughts about which points converge to red, which converge to blue, which converge to green? It's okay if you're wrong. How would you describe in this picture which points converge to 1? The point. I'm sorry?
The positive numbers converge to 1?
That's one way to say it. It's the positive numbers, but there's another way to say it.
The points closest to 1.
The points closest to 1 go to 1. Isn't that a great property for an algorithm to have? It takes you to the nearest root. So which points do you think are going to go to the red root?
Those closest to the red root.
Yeah, so if I divide the plane into thirds, this should be the red zone, this should be the blue zone, and this should be the green zone. Does that seem reasonable? Turns out it is not the solution. And you have a beautiful fractal pattern. So if you've never seen fractals before, there's going to be some links on the next slide. The situation is far more complicated. I will risk trying to play. Hopefully it's showing. And so one of the ways you actually calculate stuff like this is you can use Horner's algorithm to make the computations a little bit more efficient. So this is zooming in, and it's absolutely remarkable that very small changes in the initial conditions greatly change which root you converge to. There's a tremendous amount of symmetry going on here. There's a lot of group structure going on in the background. I will pause this here. And swing back to. And so, it's quite strange because, over here, I'm very, say a point right here, I'm much closer to the red and the green roots, but somehow I end up going to the blue roots. And over here, if I'm going to the red root, but if I move over just a very small amount, I end up going to a green root. So it's really fascinating, this sensitivity to initial conditions. And this is one of the big themes in a lot of mathematics, that we often have extremely complicated equations where very small changes lead to wildly different behavior. I have a friend who works on climate change models. And so I'm not saying global warming is happening. I'm not saying global warming is not happening. What I am saying is he has noticed that some of these models have very different answers in terms of what happens if you change the values of some of the parameters by very small amounts. And so you want to be very careful when you're doing mathematics. How sensitive is the answer to our number? Our number, when we're doing the square root of 3, we got a terrific approximation. The number of digits is phenomenal with this rational approximation x5, but x5 is not the square root of 3. Is there going to be an impact in the model if I make an approximation like this? If I'm sending a rocket from the Earth to the moon, no, there's not going to be enough time for that to really have an impact. But for other things, yes, small differences will make a huge difference in the limit. So hopefully people have seen the Mandelbrot set before. If you want more details on stuff like this, again, always happy to chat. I put some links to slides and talks I've given on the subject. I've also put some links onto some Zooms. I forget which one is the best one to do for the extreme zoom. I'll just randomly try this one. A lot of these have cheesy links. The video is not available anymore. Okay, let's try a different one. I don't know if I want to deal with listening to a Liberty Mutual commercial, but I love Liberty Mutual, of course. So let's see if we can quickly get a skip ad. Okay, so this is zooming in 10 to the 144 times of the Mandelbrot set. This is one of the most famous fractals. And as you zoom in, you see this incredible amount of self-symmetry. You keep seeing the same shape again and again and again. And again, computationally, to just do this, it's an incredible challenge. Your Horner's algorithm saves us a lot of computations. Any tricks you can do become very valuable. And the scale we're at is phenomenal. The colors are basically related to how quickly, when you iterate, things go off to infinity. And just zooming in, zooming in, zooming in, zooming in, and as you keep zooming in, you start to see the same structure at smaller and smaller scales. And so I always find these things fascinating in terms of just how far you go. And in the upper left, you're giving us some sense of just how much we've zoomed in. We're at like 10 to the 38. And so in the interest of time, we're now at 10 to the 130. And you're just zooming in, zooming in, zooming in. 135. And we should be seeing the Mandelbrot set coming in very soon. And there it is again. So there's a lot of wonderful mathematics behind all of this. And so just to quickly end, we've been talking today about finding the roots of polynomials. We can find them explicitly for degrees up to 4. For higher degrees, we cannot do this. In a next class in modern algebra, you would actually talk about the proofs of those. I've given you 2 videos to listen to if stuff like this interests you and excites you. I'm always happy to talk to you about consequences of this. For Thursday's class, I'll probably talk about some of the applications of small differences between being exactly this rational and being this irrational number. So these numbers we're looking at, they have really interesting properties. All right, so this is a good place to stop. I will stay on for a couple of minutes in case anybody has questions on things they want to talk about.